So this is a quick review of topics for exam 1 here in abstract algebra. What was in chapter 0? I'll go in the order that it was in the book, not the order that we did it in class as far as your homework went. It started off with, well, the division algorithm, whose proof was based on the well-ordering principle. What was the well-ordering principle? It was the principle that every non-empty set of positive integers has a smallest member. And using that fact, which we took to be an axiom, we assumed that was true. We didn't try to prove that. You could prove the division algorithm. The division algorithm proof's kind of long, but I said you should understand it well enough to reproduce parts of it, or maybe if I give it partially to you on the test, you could fill in the reasons. So you should study it. We also were led to the idea of the GCD, greatest common divisor of two numbers, two integers. The GCD is a linear combination theorem. The GCD of two integers is a linear combination of those integers. And in particular, what that means when A and B are relatively prime, it means their GCD is 1. And that means that 1 can be written as a linear combination of A and B as AS plus BT for some integers S and T. And that was a really useful thing for a number of proofs. Also, you'll find Euclid's lemma. If a prime P divides A times B, then it must divide one or the other, or both. That's not true if P is not a prime, and you should be able to come up with examples of that. The book also does talk about the fundamental theorem of arithmetic in terms of prime factorizations. And I also, in one of the lectures, talked about Euclid's algorithm or Euclidean algorithm for finding the GCD. That was in a lecture. The textbook doesn't really talk about that. Then modular arithmetic, there was a lot of stuff in chapter 0. Both calculations and basic proofs related to modular arithmetic. Also in chapter 0 was induction, examples of induction, and there were 2 principles of mathematical induction. We only really focused on one of them. And I think that would be the only one you'd have to focus on for the test. Then the end of the chapter got into 2 other topics. Equivalence relations, equivalence classes, which partition the set into disjoint subsets whose union is the whole set, and functions, one-to-one functions, onto functions. If it's one-to-one and onto, it's got an inverse function. Those kind of ideas was the end of chapter 0. Chapter 1 was a shorter chapter. Basically, examples of groups without a formal definition of group. Examples of groups without giving a formal definition. Main example we studied was D4, symmetries of a square. Though in one of the lectures I talk about D3, symmetries of an equilateral triangle. which is technically a simpler group. D4, also called the dihedral group, has 8 elements, 4 rotations, 4 reflections. D3, dihedral group, symmetries of an equilateral triangle, has 6 elements, 3 rotations, 3 reflections. And there's examples of other geometric symmetries that you try to identify in the problem set. Probably I would not put those pictures on your exam, because we didn't really focus on that. But certainly D4, maybe even D3, something you should be familiar with. Obviously, I'm not going to have you come up with the entire Cayley table or anything like that. But you should sort of be familiar enough with the Cayley table that, I don't know how to say it. Maybe if I put the Cayley table on the test, if I made a copy of it, you should be able to work with it. Or you should be able to think about individual products and what are their inverses pictorially, if necessary. Chapter 2 is the formal definition of a group and basic properties of groups, which include, for example, the fact that the identity is unique, inverses are unique, cancellation laws, left cancellation, right cancellation, and properties of exponents. For example, a to the m times a to the n equals a to the m plus n. E.g. means, for example, it's Latin for example. Chapter 3 gets into, first of all, order of groups and order of elements. Order of a group being the number of the elements in the group. It's infinite order if there's infinitely many elements. The order of an element being the smallest positive power, bringing you back to the identity if there is such a smallest positive power. If there's not, then you say it has infinite order. Subgroups are more than just subsets. They are groups in their own right with respect to the same operation. So that also means, for example, Z4, even though it's a subset of Z5, Z4 is not a subgroup of Z5 because the operation is different. In Z4, the operation is addition mod 4. In Z5, it's addition mod 5. U4 is not a subgroup of U5, even though the elements of U4, which are, 1 and 3, are also in U5. But the operation is different. Multiplication mod 4 versus multiplication mod 5. So it's more than just being a subset. It's also a group in its own right with respect to the same operation. That's important. Subgroup tests. One-step subgroup test, two-step subgroup test, and finite subgroup test. We mostly emphasize the 1 and 2-step. I think that's probably what I'd test you on if I put that on the test. And I probably will put a subgroup test problem on the test. We've emphasized it a lot. And then specific examples of subgroups, which include, for example, the center, Z of G, the set of all elements of G that commute with everything else. Centralizer also is in there. Centralizer of an element is the set of everything in G that commutes with that element. The center is a subgroup of G, so is any centralizer, and also the center is a subgroup of any centralizer. If you commute with everything in G, you're going to commute with A. They're both subgroups of G, and the center is the subgroup of any centralizer. There are lots of centralizers. For any A, I can make a centralizer. There's only one center. Different A's could have the same centralizer, but in general, they could be different. Cyclic subgroup generated by A, probably our most important subgroup. We also did an example with conjugates. If H is a subgroup, then its conjugate is a subgroup for any X in G. This is the set of all elements of the form X times something in H times X inverse. We did this. Running low on time, chapter 4 was about cyclic groups. And all the properties of cyclic groups. Lots of properties. If A has order n, for example, A to the I equals A to the J, if and only if n divides I minus J. There's the fundamental theorem of cyclic groups. Any cyclic group of, say, finite order has exactly one subgroup whose order divides the given order. Figuring out generators using the Euler-Phi function. Chapter 5 is about permutation groups. Groups are permutations. Permutations are functions. You should be comfortable with either array or cycle notation, finding inverses, finding orders, using the LCM property when you've got disjoint cycles that are being multiplied to figure out the order. Doing an example like we did today, maybe a little simpler than what we did today. Figuring out the number of ways of doing things. Sn is all the permutations on any group of n objects. An is all the even permutations. What is an even permutation? What is an odd permutation? There's pretty fundamental things to know to say you are learning group theory. In fact, originally group theory was all about groups of permutations. It wasn't this really abstract thing. So it's historically important as well. And chapter 6, isomorphisms. The first half of that chapter.